Good morning, and thanks to the chairperson, and also thanks to the organizers for giving me this opportunity to show some of our recent results on which we are working at IIT Delhi. What I am going to talk about a little bit different than the three previous speakers. So we are going away from 2D now and coming to 3D. And most of the measurements which I am going to discuss, the analysis also, should be familiar even to the students. So what I am going to discuss only some diffraction studies, okay, not very high-fi. So what we are going to trying to understand is the following. So the magnetic and structural properties of some of the exotic materials which are very important for applications. Having sodium in it, and there the sodium transport is playing a crucial role. So the outline is that what are these materials and what we are trying to understand at IIT Delhi. This is what I am going to present in next couple of minutes. These sodium superionic materials, the formula is written here, so you can see the sodium and transition metal. This doesn't like, okay. M prime is the transition metal, and mostly we are, so the M primes, mostly we are focusing on iron chromium in this particular case. The sodium concentration is also important here, that varies the Ux value from 1 to 4. And here the Ux is also can be phosphorus, sulfur or silica. These materials are having very high sodium transport properties mechanism, and therefore these are very useful for battery applications. Okay, I am not going to talk on battery part here, but the structural part, if you look into it, I will show you in the next slide, having the 3D polyanionic stable and open structure for giving the path, easy path for the sodium to transport during the charging and discharging of your battery of your mobile phone, your laptop and so on. And these materials are also showing very interesting structural and magnetic properties. So as a physicist, we should also understand that, and that's what we are trying to do in this particular case, where some of these materials are showing antiferromagnetism at low temperature, below 50 Kelvin or so. And also it was reported, and we also found that it is not really a pure antiferromagnetic, it is actually showing a complex behavior where there is a competition between antiferromagnetism and ferromagnetism both. And from the structural point of view, what we saw is that most of these materials are stabilizing in the rhombohedral phase, but also there is a lowering in the symmetry, and some of these materials also showing the monoclinic symmetry. And what we found recently is that there is a transition between these two, and this transition is very critical, very important for the battery performance as well. So that symmetry lowering is what we found is mainly due to the sodium ion ordering. So if you look at the structure, again the same formula. The structure of course is bit more complex, and as I said is the 3D open structure. I will try to explain a bit here. So the sodium here is having at placing at the two sides, so Na1, Na2, and as I said, this is mostly in the rhombohedral structure, and what is there is this kind of structure M prime PO4 thrice. So this is what is the covalent skeleton type structure, where there are M prime O6 and PO4 polyhedra are connected, where octahedra and tetrahedra, they are sharing the corners and making this type of unit what we call lantern unit, M prime PO4 thrice. Okay. And you can see here these PO4 tetrahedra and also M prime O6 octahedra. They are connected, sharing the corners and making this type of structure. And the other part is where the sodiums are sitting, and in this particular case the sodiums are sitting at two different sites. Okay. So there are two distinct sites for sodium, and this is 3D structure having different channels for sodium to transport. And what we found is that this symmetry change due to mainly sodium ordering, that's what we have recently studied using synchrotron X-ray diffraction. So this is what I mean by structure or the ordering. So the rhombohedral phase here is shown as I said before, and this is the famous example long back studied by Goodenough. And this is the monoclinic structure, The interesting part is that the conduction pathways for sodium transport changes, and mainly because the sodium sites, so you can see here there are 2 sodium sites, however in monoclinic phase there are 3 sodium sites, and therefore the paths are different in different structures. Okay. So mainly if you look at this formula where the Ux can vary from 0 to 3, and what was observed that the rhombohedral structure is stable be in this Ux range, however the monoclinic structure is stable when the Ux value is around 2. So when the Ux value is around 2, then that means the sodium is 3. So whenever you have sodium content close to 3, you can stabilize these materials in the monoclinic phase. And when you have monoclinic phase, of course, then there are 3 sites available for the sodium, particularly for Na1, Na2, Na3, and then there are different conduction paths in this particular structure. So in the recent past, in fact long back, there were very few studies where people talk about how the battery performance changes when you change the structure of your cathode material in particular. So for example, the superstructure in this particular phase of this cathode material LFP is a very famous material. Everyone is having at least one LFP material in the pocket, maybe more. So that superstructure, if you can stabilize in this particular material, will accelerate the battery performance. There was another paper where the working potential, so what we talk about the battery, 3 volt battery and so on. So this voltage also can be changed when by changing the sodium or the vacancy ordering in this type of materials. Also there was another study where in this Nature Communication they talked about structural order disorder transition that actually enables the fast sodium transport or the fast sodium storage. So that you can even charge your battery very fast. So with that motivation, we started working on some of these materials, also trying to understand the magnetic and the structural properties of these. So I will show you the results on 2 materials which we also use as cathode for sodium ion batteries, but here I will be talking about magnetic and structure part of it. One of them is the sodium iron phosphate sulfate. So the PO4 thrice, 2 units of PO4 we replaced with SO4. So you can see here PO4 1 unit and SO4 2 units. And of course then to have the charge neutrality, you have to then change the sodium content. But of course the first thing after the synthesis, all these materials are synthesized by either solid state reaction method, the simple route, or the sol gel method. So the first thing what we have to do is X-ray diffraction, then do the ritual refinement, extract the parameters, and then try to understand the structure. So this is the X-ray diffraction lab based system fitted with the rhombohedral. This is, you can see the sodium is 1, so it is expected to get stabilized in rhombohedral phase, and that's what we have found out here, the rhombohedral phase. All the parameters, the latest parameters and all are consistent with the reported parameters. Then what we did is the neutron diffraction at BARC with this particular lambda value, and what we can see here is that we were able to again fit with the rhombohedral phase, and of course neutron diffraction is more sensitive to oxygen, for example, and the sodium, which are being the lighter elements. We were able to find that there is a bit of deficiency of sodium and oxygen in the sample, this which is of course common in these sodium based materials. Then we were interested for this particular case in study of magnetic properties. So what we did first is the magnetization versus temperature, and you can see in these 2 panels the MT curves taken at 2 different fields. So one of them is at 500 OE, and in MT of course what we have to do is one is called zero field cooled and one is field cooled. And normally in pure antiferromagnetic materials, what we have to see is, what is expected to see is that at certain temperature both Fc and ZFC they should go down, okay, and they should follow each other. However, what we have seen is that the ZFC Fc there is a large bifurcation below this temperature which is close to 50 Kelvin, and then when we increase this temperature, this field from 500 OE to 10 KOE, this suppression, the bifurcation got suppressed. So that tells us that okay, there is something interesting, not only the antiferromagnetic ordering below this temperature, there is something more than this. Then of course when you plot chi inverse versus temperature and do the fitting, the Curie-Weiss law, this will give you some parameters, will help you to identify what exactly the magnetic ordering is in your sample. So, the theta value is negative, that gives you the idea about the antiferromagnetic ordering present in the sample. Mu effective of course is close to 3.9 from the experiment, and the calculated mu effective also 3.9, considering the iron 3 plus in intermediate spin state. Okay, so this is good, and if you of course consider the iron 3 plus in high spin state or low spin state, you can make some combinations and also get the value mu effective, which is the experimentally obtained value. Now, what we next did is the magnetization versus field, and of course, this is unsaturated expected for antiferromagnetic ordering. But what is more in it is that there is also small hysteresis at near 0, 0, and that tells you that there is also contribution from the ferromagnetic ordering in it. So, antiferromagnetic ordering predominantly and weak ferromagnetic ordering present in the sample was concluded at this stage, but of course, this magnetization not enough to conclude something at this point. So, what we did is the neutron diffraction at BARC Dhruva reactor as a function of temperature. So, you can see from room temperature to 5 Kelvin, and what we found out is that if you look at the lower panel where we subtracted the data 5 Kelvin minus 60 Kelvin, 60 Kelvin of course from the magnetization we saw that the transition is happening at 50 Kelvin. So, 60 Kelvin is above that transition, and what you can see is that there are some extra peaks which are the indication of the antiferromagnetic ordering present in the sample. Then this confirms the antiferromagnetic ordering, and of course then by doing the fitting and the propagation vector, the magnetic propagation vector which is 0, 0, 0 with respect to the nuclear shell that we have already studied by X-ray diffraction. We did the Rietveld refinement, so 60 Kelvin and 5 Kelvin, and which we are showing here, and then some more details of the fitting with the fitting parameters, the R parameters and so on, which are reliable factors. What we found out is the magnetic structure. Okay. So, if you look at the ordered parameter from here as a function of temperature, it changes exactly at the 50 Kelvin where we saw the transition in magnetization. And then of course, the ordered magnetic moment here from the neutron what we got at 5 Kelvin is 3.8, and the effective moment that we got from magnetization was also 3.9, which is very much in agreement. And when we look, then of course, when we see the ordering, the structure, the magnetic structure, what we found out is that this is pure antiferromagnetic ordering, no net magnetization per unit cell, again the per unit cell, and the moments are mostly lying in the AB plane, the component along the B axis. So, you can see here this is B, this is C, and the structure was found out to be A type antiferromagnetic ordering, where you can see the moment in each AB planes are parallel, and then along the C axis it is antiparallel. So, this was concluded from the neutron studies. So, neutron of course is telling us that this is pure antiferromagnetic ordering, magnetization is telling that there is something complex. So, what next we have to do is the AC magnetic susceptibility. That is what we did. The chi prime and chi double prime are plotted here as a function of temperature and at different frequencies at very low excitation field of course. And what we can get from here is that there is reduction in the intensity of the signal in AC prime. Okay. However, there is no significant change in the shift in the peak position. So, of course, if there is a significant shift in the peak position, we can do the analysis, the relaxation behavior, and we can conclude something more. But from here what we can conclude is that if there is a reduction in the intensity of chi prime signal, there is a signature of the glassy behavior in the system. The other part is that the chi prime for pure antiferromagnetic system, the chi prime signal should be 0. Okay. However, we got the significant signal of chi prime which is of course the out of phase component, and that gives us the idea that there is a glassy nature in the system in this particular sample. So, because as I said the chi double prime signal should not be there for pure antiferromagnetic ordering. To confirm this further, of course, we did two more measurements. One is what is called TRM, where you take the sample at room temperature, then you cool it in the field. So, this field cooled, wait for some time, remove the field and then measure the magnetization. And that of course will decay with time, and how it is decaying, you do the fitting and then can conclude something by extracting some of these parameters from this exponential model. And from these values of TR and the eta, what we found out that these values are lying somewhere which is suggesting for the glassy magnetic phase. Again another measurement, that is what is called aging measurement, where we do a little bit different, or what you can say opposite to what we did before. So, we actually cool the sample in the zero field, then wait for some time and then apply the field and measure the magnetization. Okay. Again this is, as I said, opposite. So, you use the same or similar exponential model, you have here minus sign, earlier it was plus sign. You do again the fitting and then extract the parameters, and that will again give you the idea about the magnetic ordering. So, what we again found out from here is that these parameters are lying somewhere where this is indicating that there is a spin glassy behavior in this system. So, concluding this sample, this study here, that we found in this sample the antiferromagnetic ordering and the ferromagnetic ordering competing to each other. Now, going to the next sample, where now we have Na3. So, as I said, when the sodium concentration is close to 3, you will be able to see the reduction in the symmetry. So, that means from rhombohedral to monoclinic. So, this particular sample, of course, very interesting from the magnetism point of view, which I am not presenting here, but from the structural point of view, what we did first is the X-ray diffraction, again simple. Again this is the structure rhombohedral, and the ritual refinement could not fit a peak here. Okay, this is what is called the superstructure peak, right. So, then that tells us that there is something more. So, this superstructure peak is coming from the sodium ion ordering. This is what we are concluding here, but of course, we cannot conclude without doing the detailed analysis or detailed measurements. So, for that what we did is then we changed the refinement, the space group of refinement. So, going from rhombohedral to monoclinic now. So, the C2 by C space group we have used, and again the same X-ray diffraction, but now you can see that this superstructure peak has been fitted well. Okay. However, more than this, what you can see here, the small peaks in this particular range, you can see the fitting is not good in this case, and for that what we have to do is, of course, then you have to make the supercell. Okay. So, here what we have used is only 4 formula unit in the unit cell, and then if you make the supercell, of course, then you increase the number of, so this we went from 4 formula unit to 12 formula unit, and then you can see we were able to fit all the peaks, and the refinement gives us the lattice parameters and the other parameters which are consistent with the monoclinic structure. So, what happened here is that there is just lowering in the symmetry from rhombohedral to monoclinic, okay, and that is of course expected as the sodium concentration in this particular case is close to 3, and that was predicted long back even by Goodenough. But how this is going to affect the battery performance, of course, that is not part of this talk, but that is what is our motivation. What we then thought about that, okay, how this symmetry get changed with temperature, because these materials we have to operate or we have to test at different temperatures. Your battery should be operated in large temperature range. So, what we have done is the differential scanning calorimetry, and what we found out is that there are transitions at 2 different temperatures. So, one is close to 350 and the other is close to 450 or 460 around. Of course, one is called one is endothermic, one is exothermic, and what you can do is the first glance it will give you the idea where the major things are happening, and that can be done, that can be calculated by the calculation of enthalpy change. So, of course, then you take the area under the curve and change the unit, you will get the delta H value. So, delta H value for this transition, what we call alpha to beta, is significantly larger than the delta H value for this transition, which we call beta to gamma. Okay. So, that indicates at the first glance that in the structural ordering or in the structure, the major things are happening at this particular transition. Okay. So, the most of the structural and the sodium ion rearrangement is happening at this first transition, what we call alpha to beta, okay, and which is around 350. So that of course motivates us to probe more, and how we can probe, we decided to probe by X-ray diffraction, again the simple technique everyone knows. But of course we don't have the laboratory, in laboratory we don't have the synchrotron, the temperature dependent X-ray diffraction with such high resolution, because you also want the high resolution. So we then did temperature dependent X-ray diffraction using synchrotron radiation facility at RR cat, and you can see here the 2 theta and the temperature going from 300 Kelvin, so room temperature, to around 520 Kelvin or so, to study across the transition. And what you can see here, of course, so what you can see here, at the room temperature we were able to fit this with monoclinic, and then at 358 Kelvin you can see this peak disappeared. Okay. So that is what is the superstructure peak that I showed you, and then up to 523 this peak is not there, and then when we come back to room temperature this peak should come back. So you can see this superstructure peak again. Okay. So if you compare this with the DSC, this is the DSC figure that I showed you, and this is the map for this temperature dependent X-ray diffraction, and what you can see here is that this superstructure peak actually disappears at the transition which was indicated by DSC. Okay. So this superstructure peak disappeared, and then of course there are many other changes that we have tried to probe. So this 300 Kelvin and then the highest temperature we were able to fit with the monoclinic phase and the rhombohedral phase respectively, and extracted the parameters, which of course this change is happening mainly because of the breaking of threefold symmetry going from rhombohedral to monoclinic. And then to understand this more, as I said before, in the rhombohedral phase, in the rhombohedral phase there are 2 sodium sites, as I said in the very beginning, sodium 1, sodium 2. However, in the monoclinic phase there are splitting of these sites, sodium sites. So the sodium 1 site splitted into 2 and sodium 2 sites splitted in 5. So you will have more complex crystal structure, and that is what we were able to trying to understand. So since I have less time, what I wanted to focus here is that the rearrangement of the sodium ions in the structure, you can see in this alpha phase, that is what is the monoclinic phase, the ordered one. You can see here these are the vacancies in this, you can see the hexagonal, and in between there is vacancy here. However, in the gamma phase, that is the rhombohedral phase, the high temperature phase, there is a statistically distribution of the sodium ions. So you can see even in the hexagons the sodium ions are present, because now there are more number of sites where the sodium ion can go and sit. We then of course did more study, more analysis to find out how the sodium ion redistribution among these sites. So you can see in the first panel, so the sodium occupancy, this is the temperature, the blue one is the DSC curve that I showed you before, and you can see this is sodium 1 site and the sodium 2 site. We saw that how the sodium ion rearrangement happening with temperature, and you can see the sodium ion moving from, so here this is fully occupied site and this is partially occupied site, and then you can see sodium ion going from sodium 1 site to sodium 2 site. So this is occupancy decreasing and this is occupancy increasing, and of course above this transition more or less similar. So that was one observation here where we saw the rearrangement of sodium ions among the sites available. Then of course the lattice parameters, so the A, B you can see here for the monoclinic phase should be different. So A is decreasing and B of course more or less constant, and then suddenly it collapsed and transformed to the rhombohedral phase, where in C, along the C axis also you can see a drastic change at the transition temperature, and then of course it goes almost linearly, that gets reflected in the normalized volume as well. So we wanted to understand what is happening in the C axis. Of course then we tried to calculate the bond lengths and so on, and we found out that there is elongation in the C axis for when we go from monoclinic to rhombohedral structure. Then this is the last slide. So here what we have tried to understand is the intensity. So you can see the integrated intensity of this particular superstructure peak. I said that this will this disappeared at the transition temperature. So you can see also here going from room temperature to high temperature, the intensity here at the transition temperature disappeared. So this is what we have plotted here. Then use some formula, the equations here. First try to fit with the power law, which could not fit. Then we use the phase fraction model, which is the sigmoidal formula. So we use this equation and try to fit, which is the blue dotted line. That will give you the idea about the transition temperature that comes out around 349. Which is also consistent with other analysis where we have plotted the integrated intensity of these peaks. You can see for monoclinic should be splitted in 3 peaks, and for rhombohedral this is 116, which is somewhere close to 15.8. And also the 2 theta values here. So you can see a discontinuity here, and also the FWHM and the derivative of this 2 theta also giving you a sharp change around 350 Kelvin, which is consistent with this analysis as well. So what we figured out from here is that the rearrangement of sodium ions between the sites is mainly happening at this particular transition, which was also observed in DSC. So with this, let me conclude by saying that the first sample, this sodium iron phosphate sulfate, we did detailed neutron diffraction and magnetization studies and found out that there is a complex magnetic structure in it. And the second example of iron chromium, where we found out the order disorder transition happening around 350 Kelvin. So which is roughly 50 Kelvin above room temperature, is very crucial even for the battery applications, where our battery temperature in peak summer goes to roughly 100 degrees centigrade. And so this is what was observed, the rearrangement of sodium and more importantly that what I said, the lantern unit where M prime PO4 thrice, that structure did not get affected much. So our conclusion was that this ordering and the symmetry in the structure is playing a crucial role for battery applications, and that's what we are now planning to focus more on it. With this, of course, the work what I presented, the first and second was done by Manish and Madhav respectively. The neutron diffraction we did at BRC in collaboration with Professor Yusuf and Anup, and the synchrotron XRD we did in collaboration with Dr. Arsena. So I acknowledge from all of them, and of course the funding agencies. So with this, thank you for your kind attention.
Thank you, Professor Dakka, for this interesting talk. Now, yeah.
These materials are, what is their ionic conductivity?
Is 10 to power minus 3 minus 4 in that range. Siemens per se, yeah.
Room temperature.
Yes. So these are like, that's what is a super sodium superionic conductor.
So are they hygroscopic?
Not really, where they are stable, but of course they have sodium. So if you expose for long time in different environment, something may change.
Nice talk, sir. Sir, I have a question that you mentioned in some slide that ordering momentum of in antiferromagnet versus temperature. So what do you mean by, how do you define this ordering moment in antiferromagnet?
No, so see, the overall moment should be 0, right? So if I go back, so okay, so from the neutron what you are saying, right? So the moments are ordering in the plane, right? So what I showed the structure in the AB plane, the moments are in particular direction. So for one plane it is oriented in like this, so the other layer it is opposite.
But these spins are opposite to each other.
Yes, yes, yes. So the overall movement should be 0 or close to 0.
In each plane there are two like spins are oriented towards opposite sides in each plane, right?
No, in each layer it is parallel. In each second layer it should be opposite.
Okay. Thank you.
Very nice talk, Rajendra. So I was just trying to understand this R3 bar C when you did the refinement. Some of the some of the peaks, to understand them better, you had to increase the unit cell, right, to include 12 formula.
So that was monoclinic.
Sorry, monoclinic.
Yeah.
So you have to within the same space group to describe those peaks better. You had to increase the size of the unit cell.
Yeah.
But the structure, the phase was the same.
Yeah.
So, and then when you relax, there were little structural. So the fact that the unit cell increased, were there rearrangements in some structural parameters? Like how did it help to describe those peaks better? Were there some rearrangements, some in the structure when you allowed that relaxation to happen, or?
Yes, yes. So this was monoclinic structure. So you have to, so to fit those peaks around 15.8 2 theta values, we had to then increase, so make the supercell and increase the Z values. So, but in the same space group. So that tells us that how the sodium ion rearrangement happening among the sites available, which are now many more as compared to the rhombohedral phase.
Okay, so that was the degree of freedom as well.
Yes.
Okay, just as a curious, another observation, like from an outsider into this field, like for the sodium ion conductor, would you like it to be at room temperature, the supraionic conductivity, or around 350?
No, so room temperature, of course, but see, we operate the battery at least I would consider 50 or even 100 degree above room temperature and below room temperature. So 200 to 400 range I consider for the battery operation in extreme conditions like around the globe.
200K to 400K.
Yeah, 200K to 400K. Yeah.
Thank you, very interesting.
So if your battery is, let's say, around room temperature, the actual battery temperature is slightly higher, maybe 10, 20 or 30 degree higher. So considering that, 100 up, 100 down.
Any other questions?
Thank you, Rajendra, very nice one. So, small question about your synchrotron neutron scattering. So, you mentioned that you can subtract out the. So, I've never taken such data. So, you can subtract out the 5 and 60 Kelvin data to get these two things. So, what is the? How do you conclude that this is a signature of antiferromagnetic?
No, so you don't have to do that to conclude this, first of all. So what you will see in neutron diffraction when there is appearance of antiferromagnetic ordering, so from paramagnetic to antiferromagnetic ordering, you will see a new appearance of new peaks, new diffraction peaks. Okay, so that is clearly there, but just to enhance for the clarity, we can subtract one data from each and then can see the change. So everywhere else it should be 0 because you are subtracting one from the other. So nuclear phase is same in both the cases. So it should be straight line like just noise. And wherever there is an appearance of new peak, that should be visible clearly.
That could be signature of a ferromagnetic phase.
No, no. So in ferromagnetic phase, you will just see the change in the, so no appearance of new peak will be there in neutron diffraction for ferromagnetism. It will be just change in the intensity up, down, or maybe some broadening.
So para to ferromagnetic transition, you will not get any new.
No, you will not get any.
Are there any questions? If not, let's thank Professor Taka once again.
Thank you.